Lesson on unit 1718. We're going to look at box C here. We're going to find out how you take the derivative of the natural log function. And as we do this, we're going to build on what we talked about last class, how you do the derivative of an exponential function, specifically with base E. So now we're going to look at logarithms with base E, and then we're going to move on in box D to talk about what you do if your base is something other than that magical number E. So last time, when we were looking at functions that look like this, we said that the derivative was just the original function back again, and that was the great thing about using E as your base here. Now, how can we use this to try to figure out what the derivative is if you're doing the natural log here? So let's start with the function that we want to work with. We want to work with something that is y equals ln of x. Remember that ln just means the natural logarithm or the logarithm to base E. And we want to find the derivative of this. Now, what we know how to take the derivative of is something where we've got an exponent with base E. So we're going to use this trick where we take both sides of this equation that we have here, and we're going to raise both of them to the exponent with the base of E. So this will become e to the y equals e to the ln x. Okay? And I can do that as long as I do the same thing to both sides here. And if I've got e to the ln x, we remember that if we've got a base of e and we've got a logarithm to the same the logarithm of the same base up in the exponent, these two things essentially cancel each other out. So now we've rearranged this so e to the y is just equals x. So basically what we've done here is we've taken the inverse of our original function. We've gone from y equals ln of x to the inverse function, which is e to the y equals x. Now let's think about how we could take the derivative of this thing that we see right here. So I want to take the derivative of both sides of this. And not y, but e to the y. So derivative with respect to x of e to the y, and derivative with respect to x of just x. The right-hand side is pretty easy here. If we're just taking the derivative of x, what's that going to be? Just 1. It's the left-hand side that's a little bit trickier here, because what we have is we have a function, e to the y, and y is itself a function of x. So we have to use chain rule here because y is a function of x. So I'll just say y is a function of x, so we'll have to use the chain rule. But that's okay because we learned how to take derivatives of exponential functions using the chain rule in our last lesson. So we know that if we take the derivative of e to the y, we'll just get e to the y back again, and we multiply that by the derivative of that function that we have up in the exponent. So the derivative of y, we'll just write that as y primed. Okay, so we get e to the y times y primed equals 1. Well, what is e to the y? This line right here tells us that e to the y is just equal to x. So if we sub that in down here, we get that x times y primed is 1, or y primed is 1 over x. And there's our derivative. So y primed equals 1 over x when y equals ln x. Okay? So the derivative of ln x is just 1 over x. And there's our first derivative rule. Okay? And if we want to extend this a little bit, we can imagine that our function is, we have a composite function. So we've got the natural logarithm of some function g at x. Okay? Then we just have to apply the chain rule. Our derivative is going to be, instead of 1 over x, we'll have 1 over that function, g at x, and then we have to multiply that by the derivative of that inner function, g at x. So that'll be just g primed at x, whatever that happens to be. So there are the two derivative rules that you need to know for natural logarithms. Okay. All right. So we'll try a couple of examples here. Okay. So the first one here, y equals the ln of 5x. This is itself a composite function here. So let's identify what is that inner function, or that g at x function that is inside of our outer function. Our outer function is the ln, but our inner function is just the 5x. So our derivative is a pretty easy derivative. It's just 5. So let's apply that rule. Our derivative, y primed, is going to be 1 over that inner function. So 1 over 5x times the derivative of that inner function, or times g primed at x. G primed at x is just 5. So we get 1 over 5x times 5, which simplifies very nicely to just being 1 over x. Okay. So anytime you're doing the derivative of the ln of something, the ln of like some number times x, you're just going to get your basic ln derivative back, 1 over x. Okay. So let's look at something a little bit more complicated here. Our next one, we've got y equals ln to the x squared plus e to the x. Again, we're going to use chain rule, so let's identify what's our inner function, our g at x function this time around. Yeah. And then let's figure out what the derivative of that is. So we got x squared plus g to x is our inner function. Our derivative of that is just going to be, well, we can do this term by term, so it's going to get us we don't need product rule because we're just adding these two things together. So it's just the derivative of one plus the derivative of the next one. Yeah, and e to the x is really easy because it just gives us e to the x back again. All right, now let's put this into our logarithm derivative rule here. So y primed is going to be, again, it's 1 over that inner function. So the inner function was x squared plus e to the x. So I'll put that down on the bottom. And then I multiply by that derivative, which is 2x plus e to the x. And I make sure I put that in brackets so that I remember to multiply by the whole thing. And there's my derivative. So, and I would probably clean this up a bit by just writing it as a single fraction here. 2x over e to the x. Sorry, 2x plus e to the x over x squared plus e to the x. Okay. Now, our next one here, I've got y equals ln x over x squared. So what rule are we going to have to use here? Austin, what do you think? We could use the quotient rule, or we could use the product rule. And in this case, the product rule is probably easier. So we're going to want to rewrite this as ln x times x to the negative 2. Now, if you want to use the quotient rule, go ahead, use the quotient rule. I just like using the product rule in cases like this. I think it makes it a little bit easier. But choice is yours. Now, we don't have to use the chain rule, okay, because when we look at our ln function here, we've just got straightforward ln x. So we're just using the product rule here. We've got u and v, and our derivative is going to be u primed v plus uv primed. So let's just go ahead and work out our derivative here. Y primed is going to be, let's see, derivative of u is ln x, so we just apply the rule. Derivative of ln x is 1 over x. Multiply that by v, which is x to the minus 2, plus our original u, which is ln x, and we're going to multiply that by v primed. So we're taking the derivative of x to the negative 2, so let's bring down the negative 2 and subtract 1 from our exponent. So we get negative 2x squared all to the negative 3. Now, how can we simplify this a little bit? Nick.
You can change the 1 over x to the next to negative.
Okay.
And then just multiply them together.
Yeah, and we'll multiply. The 1 over x times the x to the negative 2 is going to give us, 1 over, I'm going to write it as a fraction, so 1 over x cubed. And then I can do the same thing in my second term here. I'm going to have the x to the negative 3. I'm going to bring that down to the bottom to get, it'll be all over x cubed. And then up in the numerator, I'm going to have my negative 2 ln x. And once I've got that, I'm going to want to combine these two terms together because I've got a common denominator. So when you're doing these logarithmic derivatives, always look to see if you can get a common denominator to simplify your expression. So this is going to be 1 minus 2 ln x all over x cubed. Okay? And we do this just because in this form the derivative is easier to work with if we want to find vertical asymptotes or we want to find set it equal to 0 and solve for x or things like that. Okay. So the last one here is a little tricky. We want to find the derivative of y equals ln x cubed plus 1 over x squared plus 2x plus 7. And we want the value of this at x equals 0. Now, I threw this one in because I just got finished telling you that we want to get a common denominator and we want to have one single expression so we can get asymptotes and we can solve for zeros and things like that. We don't have to worry about that if we know that what we want to do is evaluate it at a particular value of x, which is what we want to do here. So this one, we don't have to worry about simplifying it or factoring or things like that. So we can sort of expand it as much as we want if it's going to make taking the derivative easier. And the way to make the derivative easier is, well, if we look at this, our inner function is a quotient. So we would have to use the quotient rule or the product rule to do that, that inner derivative. That would be kind of ugly. Or we can simplify this, or expand it, rather, using the laws of logarithms. So if I'm taking the logarithm of a quotient, I can write that as 2 logarithms that I'm subtracting. Okay. Now if I want to take my derivative, these are much easier to take our derivative of because we just have to do, well, we can do the derivative of this first term, then minus the derivative of this second term. So we apply our rule for derivatives here. We get 1 over our inner function, so 1 over x cubed plus 1 times the derivative of that inner function, which is going to be 3x squared. All that minus 1 over our inner function, which is x squared plus 2x plus 7, multiplied by the derivative of that inner function. So 2x plus 2. And this works pretty neat because, well, this works out pretty easily if we sub in x equals 0. So let's just say at x equals 0, this whole first term is going to just go away because it's all times 3x squared. So this whole thing goes. And then over here, we're left with basically just this second term. So y is going to equal -1 times 2, all divided by, let's see, sub in 0 to x squared, we get 0. Sub it into 2x, we get 0. So just -1/2 divided by 7, or -2/7. Okay. Yeah, so sometimes applying the rules of logarithms can help you take your derivative there.